So I'm really glad to see so many people here. They put some pressure on me, I guess. I'll try to deliver. So my name is Jonas Bonér. I was part of founding this company, TypeSafe, but I also was the guy who wrote the first lines of the Akka code base a long time ago now, almost 5 years ago. We're actually celebrating the 5-year anniversary since like the first public sort of complaint, I'd say, by Victor Klang. It was sometime in June. And the product had been out with like a couple of hours, I think. I tweeted it and he said, "Oh, why don't you do it like this?" And I said, "Okay, fix it." And like yet another hour later, I had a pull request. So then we had a little small community that then just grew over time. So yeah, let's get started. I'm really not comfortable holding this mic, but I'll try to not wave too much. So we're in an era of profound change. I mean, for us as developers, things have fundamentally changed the last 10 years, or perhaps just 5 years. The users, they demand way more nowadays. I mean, the application needs to be, I mean, close to real time, at least have a real time feel. They need to be interactive. They need to be fully collaborative. The user needs to feel empowered that they own the data, they own the experience, and they have extremely low patience, right, for delays, for downtime. If the app is unresponsive, they will just go somewhere else. Also, for us as developers, like writing applications that we deploy, things have fundamentally changed as well. I mean, in the 60s, 70s, 80s, and 90s, applications were usually written to run on a single machine, running on a single core. RAM was very cheap. No, expensive. I mean, sorry, very expensive. And disk was expensive, and the network was usually very slow. Today is the inverse. I mean, the applications need to be deployed on like lots of machines, on like cloud computing and all that stuff, all running multiple processors. I mean, it's really hard to find a machine now that doesn't have at least two cores. Even my Samsung Galaxy is a quad-core device, and RAM is really cheap nowadays. We're not limited by that. That means that we can keep data around way longer. We don't need to sort of go and clean up that stuff. I mean, disk is also cheap, and the networks is really fast. So, and also businesses, I mean, really need to react to users much more now. I mean, business requirements change way more rapidly. It's a faster turnaround time for everything. So I think new requirements that we're all thrown into need new tools, and we need a new set of sort of not just platforms, but like physical tools that I mean, software, but also I mean, other practices. We need to think about software in a different way, and a lot of these sort of new ways of thinking are actually old, right? We need to go back in history and see how have these problems been solved in the past. And very often, I mean, the answer to current problems are to be found somewhere else. So in general, I think as when you look at how problems were solved the last 10 years and try to like solve them the same today, they just don't cut it anymore. I think the standard JEE like style of applications can't deliver on these new requirements any longer. So we really need a new way of writing applications, and that is reactive applications. Reactive applications, if you look at how applications need to be developed today, I think they need to have sort of 4 fundamental sort of core traits, very distinct traits in which they all sort of support each other and built on top of each other and form a cohesive story. And without any of these, if you just use 3 or 2 of them, you don't have that story, and it's really hard to deliver. So starting with event-driven at the bottom here, I can just point at one of these screens. Event-driven really mean react to events, right? An event is something that's happening in your application. It can be like something triggered from within. It can be an outside stimuli or something. And so event-driven applications really needs to be written in a way that they are asynchronous and that they are non-blocking. If you do that, then you get systems that are usually very efficient in terms of resource utilization. They tend to be very, very lazy. I mean, not do anything until actually being told. Okay, and tend to rely more on push rather than pull. And sort of a side effect, or something that sort of falls out of a fully event-driven system, is that it's usually very loosely coupled. Okay, and this is sort of forms the sort of foundation of many of the other traits here. I'm just going to actually put this mic up here because I don't want to hold this any longer. So the second important trait we have here is scalable. System today need to be scalable, and that means react to load. Okay. It can be both like predictable load, so that we can plan. Things might grow over Christmas or something like that, or it can be unpredictable load. We can get like slash dotted, and there are like unpredictable spikes, and the system needs to be able to deal with this in a nice way, and to really scale applications out. Either scaling up, meaning utilizing the multi-core architectures very well, or scale out. On cloud computing, many sort of applications, both either in virtualized environment or on dedicated hardware. They really need to do two things, and that is minimize contention. Contention is really the absolute top scalability killer. As long as if there are like many sort of threads or components or contending for a single resource, then there is wait time, right? Then there are components that can't do useful work because they're sitting there waiting for that sort of resource to be released. The second thing is maximize locality of reference. That means that the data is close to its processing context. That is, they don't like shuffle data around and so on. And if you look at how modern, for example, like CPU architectures work now, is that all this really comes into play. And it's really, for me, the way I look at it is that it's really no difference if you scale up and out. It's really all scaling out. And either you scale out on multi-core, these distinct processors that you can almost look like being like small, tiny machines, right? Or you scale out in the large onto machines that hold all these sort of tiny little machines. That's one way of looking at it. And the important thing then is that you have one single unified abstraction for all of this. You don't want two ways of solving that basically same problem, right? And I truly believe that the only way forward to solve this in a nice way is to adopt a fully share nothing architecture, where I mean, because in the true share nothing architecture, then data is so like data that is used together are like put together, so you maximize locality of reference. And also, if you have a single writer, then you can adhere to the single writer principle, in which that often data can be written and read like completely without contention. So that is, I mean, all this is something that we thought hard about and sort of forms the basis of Akka. So I'm going to tie all this into the Akka story in a second. Resilience is the third very, very important trait, and that's something that really makes me sad when I'm out. I mean, meeting clients the last like 5-10 years, and was actually the primary reason for me to create Akka. That I think the way resilience is looked upon is fundamentally broken. Right? It's usually something that we try to avoid while we develop our application. And once we go to production or I mean, sometimes in staging, but often in production, we just feel like, we just think, oh, what about resilience? We just ask the ops guys just turn on clustering in our app server and hopefully things will work, right? It's not a like sustainable strategy. I really think that it can't be bolted on afterwards. It needs to be part of the design of the application from day one. And if you look at resilience, I mean, things will fail, right? That's a fact of life, especially if you start adopting like scalable systems really start running on multiple machines and so on. The network can go down and disk can crash and so on. It's a fact of life that things fail. So instead of seeing it as something exceptional, like sort of embrace it as the natural state in your application's life cycle. You have the application start up. That's one phase. It might run. That's one phase. You might upgrade. That's one phase. Shut down is one phase. Failure is just another one of these natural stages in your application's life cycle. And if you look at it that way, then you can sort of have a natural way of managing it. When the failure happens, no big deal. I mean, we just go to this state that we already have prepared for, and then we fix the problem and continue. There's nothing like scary about it, really. Okay? So I really think that we need to have a fundamentally different way of approaching the problem. Share nothing is part of it, because if you have a share nothing architecture, then what you get is isolation. So you have all these components that are fully isolated, and that means that they will not lead to cascading failures. So if one component dies, it can die in solitude, right? In a way. Sure, we will sort of all feel sad about it, but the nice thing in software is that we can like revive it again, right? So you can write the system that you can restart the component, and it's like a fresh and eager guy comes up ready to do work. So I really think that's the only way to bring like sanity back to the way we deal with resilience in software. And the final trait, responsive. I mean, even if you write a system that is like, it has all these nice traits, right? So it's fully event-driven, it's non-blocking, it's resilient like crazy, like 99.999% uptime, and it's like scalable out to an infinity or whatever. It's all in vain if our system is not responsive, right? Because our users they will not want to use our application anyway if it's too slow, if it doesn't meet the expectations of the user, it doesn't meet the SLAs that are set up. So, and this is true for across the whole application. Everything needs to participate, all layers. If one layer takes too much time, slows down the execution pipeline, or then it's all in vain as well. So I really think that the applications need to be responsive at all times, not just under the blue sky scenarios when things are going well, but also when things fail. Then the responsiveness needs to be predictable. You need to know what you're dealing with in this situation, because as we just talked about, things will fail and it's natural. It can't be that responsiveness goes across the roof then. And the same thing with during spikes or whatever, things that are unplanned. So. And these are hard stuff, right? But there are good ways of dealing with it, like having a platform that deals with back pressure in a good way. That applying things like circuit breakers, have graceful degradation. If things go wrong, you can like back off. It can either be throwing messages on the floor, or it can be like presenting the user with sort of a page that says unresponsive for now, or whatever. I mean, fail whale, I don't know. But it's better to do that than slowing down the experience for all users, right? So there's a lot of tricks you can do there. And the important thing, I think, is to build really reactive applications, you need all of these four. And I'm proud to say that Akka supports them all. So let's get down to it. Starting with event-driven, then we already sort of covered sort of the basics, like asynchronous non-blocking. Loosely coupled architectures is something that naturally falls out of this, as I said, and that means that the systems are I think, in my view at least, easier to write, they're easier to understand, because I mean you can actually reason about components in isolation. You don't have this this coupled monolithic mess. And it's also easier to maintain, I think, and evolve over time. And some important things here is that if your system is event-driven, then it is concurrent by design. If you're used to writing concurrent applications in Java, like the old school way, or using threads and locks, I mean I can rant on that for an hour, but I will save you that. But I'll just say that I think that is just the wrong level of it, the wrong level of abstraction. You shouldn't have to like tinker around with critical sections. I mean, you can access these data now and whatever, like semaphores to have some counters or whatever. It's all too low level. But if you instead use event-driven architecture, then the runtime takes care of all that nasty details for you, and you tend to think in workflow. I mean, and workflow is actually application semantics, right? It's about what is the application all about. I mean, A talks to B, and he talks back to A, and he sends a message to C or whatever. So it's actually, that means that if you just think about the system in this way, and in designer applications around that, then you will get concurrency and parallelization if that's possible, for free, basically. It just falls out, which is really, really nice. So, and then I'm going to talk a little bit. The story of this talk, I'm going to go through all of the traits. I'm going to see how Akka supports them, and how you then can go about writing an application using Akka that is event-driven, scalable, resilient, and responsive. Okay. So the actor model. Akka is all about the actor model. Actor model is old stuff. It's like from '73. I think Carl Hewitt wrote the first paper on actors, it's a computational model that embodies three things: processing, storage, and communication. They are similar to objects, but they are I mean, true objects, I'd say. But they are not like your old Java and C++ object, because communication is asynchronous. Storage is share nothing. And processing is sort of single-threaded. So you don't get parallelization or even concurrency. Or concurrency you get, but you don't get parallelization with just running one actor. You need 2, 5, 10. And the nice thing is that actors, at least implemented in Akka, are extremely lightweight. So you have a design tool in which you can actually create millions of actors. I mean, concurrently living actors, which is really nice. So an actor supports 3 different axioms, and these are the things that I'm going to like base the actor, how I talk about actors about, right? So when an actor receives a message, he can do 3 things. He can create new actors. He can send messages to actor it knows that it has like references to. And it can do one sort of funky thing that is extremely useful, and that sort of brings all the dynamicity into the actor world. And that is, again, it can change its behavior for the next message. When it receives a message, it can say, for the next message, I want to redefine the way myself, right? I can change the way I should respond if the next message comes in. So if you look, the essence of an actor is that if you first define it, this stays 0. Then you can create actors, you can send messages to them, you can become, that is, redefine your own behavior. And the fourth thing that is not part of Carl Hewitt's original definition of an actor, but I think is probably the most interesting one that sort of came out of the work done by Joe Armstrong at Erlang is supervision, because you have these isolated components, like falls out perfectly to build in a sane failure model into that, and that's something Akka has also adopted. We borrowed a lot from Erlang. I owe Joe a lot. So if we start with defining an actor, the first thing you need to do is define the actor's protocol. Which messages should it be able to respond to? So you define its messages. In this case, I'm creating a simple greeting actor. It can respond to a single message called greeting that holds a string, saying who it should greet. Okay. So you just create a regular Scala class, extends actor. In this case, I'm also extending actor logging, so I can log things to the event bus. By the way, all logging in Akka is done right. It's done completely asynchronous, and it's not blocking on I/O or anything like that. And the second thing you do then is you define the actor's behavior. How should the actor react to the message it receives? Okay, so here I'm using regular Scala case, Scala pattern matching. So I'm saying if I receive a greeting message here, then I should just log it, basically. I mean, you all know Scala. I don't need to explain the details of Scala, or sort of at least. It's almost self-explanatory because Scala is so simple. Right? Yeah, I actually think it is. It sounded like a joke, but yeah.
I agree.
Sorry. Anyway, so how do I create this actor now? Okay, the first thing you do is you create an actor system. Actors, they do come in systems. A thing like Carl Hewitt said that in a presentation I saw that one actor is no actor. Actors always comes in systems in which they communicate. So you create an actor system, and on that actor system you start creating your application. You can, if you use Spring, you can see like Spring's Bean Factory, like a container for your application. Even if I don't like to use the word container. So you just use the system, and then you use this factory method called actor of, in which you first pass in a props. That's the actor configuration. You can configure the actor in many various ways. I'll show you later some examples of that. In this case, I'm just saying that I want to create an actor of type greeting actor. That's the only thing I'm doing. Then I'm giving the actor a name. Names are important in Akka. Names are, names are, for example, what defines the hierarchy of actors. Names are what we use in the configuration when you want to configure the actor system from the outside. Names are also what you can use in like runtime to look actors up and so on. Okay. So out of this actor of method comes an actor ref. So the greeter here field doesn't have the type greeting actor. It has the type actor ref. So you have a level of indirection here, which is extremely important because it's this level of indirection that allows us to do some really cool stuff. For example, when I create this actor, I don't know, of course I know now because I wrote it, but I don't have to know if that actor actually is running in process or if it's running on another machine. It all depends how it's configured from the outside. And what's really nice is that that can actually change, right? The actor can move depending on if a node went down. It can be restarted on another machine, or it can actually be moved around and so on by the runtime to optimize the behavior. So it is this decoupling that makes that possible. So the only thing you have is sort of references to actors completely decoupled from their location. This is exactly how Erlang works as well, if you know that. They have their PID, process IDs, that you send messages to. Okay? But it's also, this loose coupling is also extremely important when it comes to the failure model, as we will see, because this allows the actor to be restarted without the client knowing, because he just holds the reference to the actor, not the actual instance. Okay? So actor can form hierarchies. The top level actor in our system, is always the system guardian. Okay? So when you create an actor using actor of from the system, like here, then you get a child actor of this guardian. Okay? But each actor also has a context. It's a parameter inside the actor. So if I call the actor of method on the context, then what I'm doing then is I'm creating a child of myself. So I become the parent, and this becomes the child. So actors form hierarchies in this way, like a file system. So if you want to sort of either configure or look up the foo actor, then you just say /foo. And his child is /foo/a and /foo/a/b and so on. And what's interesting is that you can actually use this to query out multiple actors as well. You can say /foo/star, for example. That will give you an actor selection back with both of the children of foo in this case and so on. And if you send a message to that actor selection, it will reach both of them. And so on. So it's a very intuitive way of navigating your system and get a good architecture going. But the most important thing, and the reason why we do it like this, is for the failure model that we'll talk about later. Okay. So now we have defined an actor, we've created it. Let's send a message. Then we're using this funky operator called bang. But if you don't like that, you can just say write TELL, tell. because that's essentially what you're doing. You're telling this actor to run this message. This method returns immediately. This is sort of funky Scala syntax, you know. You can actually write greater dot and then bang and then parentheses. It's just a regular method call. And this method call returns immediately after putting the message on the mailbox of this actor. So that's the only job of this method. Then there's a scheduler. We call it dispatchers, that eventually, when it finds suitable, will then take this message out of the mailbox and put it into the actor's receive method to be run. He puts him on a thread and have him run on that. The interesting thing is that it's only when the actor is running on that thread, when the actual is processing the message that is actually running on the thread. Else it's idle, and then the only resource it consumes is memory. It doesn't sit on the thread, it doesn't sit holding on any resources or anything like that. And this is what allows you to create millions of actors easily. It's just a matter of RAM, and of course how much each actor is doing, because the waiting time can be severe if all of them need to use the core for 10 minutes, of course. But you know what I'm saying. So this is sending. We also have another sort of sending way of sending messages called ask. You can use ASK or the question mark operator, and this is to model the request-response sort of type of conversation that you might have. And then it actually returns a Scala future that you can wait on, not block on though, please. Instead, register callback or something, or use for comprehensions to work with that. Yeah. So if we bring everything together, this is a small actor system. I'm creating a message, and I'm creating the actor, and then the system, and then the actor out of the system, and then sending something to it. So I was planning, if the demo demons are with me, just to run a short demo here. So I need to, oops. I need to switch screen, so here we go. I can see it over there, but not over here. Okay, let's see. Let's try to, do it another way. Let's see, desktop too. No, I can't see it. That's because it's mirrored. Okay. Oh, there you go. Sorry about that. Okay. So now I can't see it on this one now.
I think you have to re-enable this sharing.
Oh, okay. Yeah, it crashed. Google Hangout crashed. We're using Google Hangout here to get the screen, to get on all the screens around here. So.
I don't think you can do anything on the other ones. You need to re-enable screen sharing and get to go.
So which one is it? This one. Okay, here we go. So, I know the resolution might be a little small, but okay. But now let's create a class here then. Scala class. This is sort of a game of ping pong I was thinking of showing. So, can you see it, or should I increase the font?
Yeah.
Is this enough? That's good. It's good? Cool. So So first, I have some snippets here to make it go faster. So the first thing I'm just doing, I'm just creating an app, and I'm creating a ball. I mean, in a game of ping pong, you want to have a ball, right? Then I'm creating the simple actor system. I'm calling it ping pong, and here I'm instantiating both of my actors. I'm calling it ping, and I'm calling it pong, and it's an instance of ping and an instance of pong. Okay. So I'm just going to import these things. There we go. So let's now create the ping actor, for example. So do that by extending actor and creating a regular class. This actor is stateful. It has like a very simple state called a counter that sort of counts as many times it hits the ball, you can say. So then I have this receive method here. So what do I want to do with that? I want to be able to sort of accept and do something when someone sends me a ball message, when someone puts that on the mailbox, and I'll get that. Okay. So what I'm doing then is in this case, can you hear me or?
Can you move the mic down just a little bit because it's hard to hear that.
Okay, sure. So here, when I receive the ball message, oops.
There you go. Receive the ball.
When I receive the ball, when I receive the mic, I'm incrementing the counter and just printing out ping counter, and then I'm sleeping. You should never sleep in an actor, but just for demonstrational purposes, that's what I'm doing here. To actually things run so extremely fast, right? Because Akka is so wickedly fast. So yeah, now I got that said as well. Okay, so here we have our little actor. Let's now duplicate this. So, oops, and then call it Pong. So here are two actors. Now, if we now send ping the ball message, okay, and run this thing, what's going to happen then? Well, first we need to compile.
Wickedly fast.
Wickedly fast, yeah. So it just prints ping counter 1. Right. I don't know if you hardly can see that there, but okay. Well, you believe me, thanks. So the reason is of course that we need both of these to communicate somehow. And now the ping actor would get the ball and it would sleep and then would do nothing. So Akka has this funky thing, this really nice thing called sender. So whenever you send a message, the sender of that message is passed along with the message implicitly, and you can just use it. It is contextual, right? So the sender can change between each reception of each message if it comes from multiple parties. So if you use this, then you should always store it away if you want to use it for later and so on. This is also why we use these parentheses to show that it's potentially dangerous, like it's side effecting. It's using a var underneath. So here I'm now sending the ball back, and I want to of course do this for these other guys as well. Probably want to do it actually before sleeping. So now let's run this again, and we'll see. So I don't know if you can see that here, but things didn't go that well either, because here it says this message was not delivered. It was delivered to an actor called dead letters. Because the thing is that if you look at this little application here, who is actually the sender of this message? It's not an actor, right? It's the object ping pong. So how can we get out of this problem? Yeah, Akka has a way of sort of passing in, passing in the sender references as a second argument to tell. So if we now write Pong here, then we bootstrap the whole thing. And if you don't like tell, you can do it like this as well. So if we now run this thing, we should have ourselves a nice game of ping pong.
I'm excited.
Yeah, I'm really excited. But oops, I don't know what happened.
Still compiling.
Still compiling?
I'm just kidding.
Weird. Did I do something wrong? I don't think so. We call all you Akka experts. What did I do wrong?
Make your Akka a little smaller so you can see the screen.
I can't.
What is the section where you're
Oh, there we go. Okay, so it was just hanging. So here we are ourselves a little game of ping pong then. So it's not. So let's go back to the slides.
forget all about it.
I probably do screen share. Here we go. Okay, so the next thing I want to talk about is the third sort of thing that the actor can do is, as I said, redefine itself for the next message that it will receive. That is using something called become. Okay, so become is a method on context. So in this simple application, what we do here is that we define two different behaviors: happy and angry, and we set the initial sort of behavior to happy by setting it like receive equal happy here. So when we receive a regular greeting, then we just print things out. But then if we instead receive the angry object here, see, we will do context become angry. This means that it will actually swap the receive from this to this. And here we have a completely different new protocol now called angry. That receives, when it receives a greeting, it prints them out, go away, and also accepts the happy message to be able to go back to the original state, right? So you can see here, this is a very nice way to model state machines, like finite state machines.
And the sender knows nothing about this, correct?
No, the sender knows nothing about it. Yeah. So Akka also has an FSM module if you have sort of more advanced sort of type of behavior and state transitions, right? But for simple things, I really like this way of modeling it. And you can use this for really advanced stuff. If an actor, for example, sort of finds out that it's overloaded, what it can do is it can sort of become a router in which it spawns up like 10 different children, starts like fanning out work instead of just doing the work himself. And this can be on different machines, right? And then if things go down, or if you like send him a message that it should actually, go back to original state, it can swap to behavior that first shuts down the messages and then go back to original state, processing all the messages himself, and so on. This gives a lot of power, a lot of dynamicity into your application.
Question.
Yeah.
How do you avoid a conflict if happy and angry messages are sent simultaneously? What happens?
Yeah, there is the question was if there are conflicts, but there is a definite order, right? The ordering of the messages in the mailbox, and that is not to be tampered with. So there is, the thing is that there is a complete non-determinism outside the actor, but as soon as the messages are put in the mailbox, it's fully deterministic. They are processed in order. And by a single thread, right? It might actually be scheduled on different threads between each execution, but still it's fully deterministic. So that's a good question, thanks. So going to resilience, I really think that, as I said, resilience is something that should be designed around, right? It's too important to be bolted on afterwards. It should be part of the application design, and this is why we have it as a like first class thing in Akka, really a first-class citizen in how you design your applications from start. And it gives you this complete sort of isolation that I talked about, avoiding cascading failures. Each actor runs in complete isolation. The only way to find out about the state of another actor or anything about an actor is to ask him, to send him a message and get something in return, asynchronously. So since actors are these completely isolated islands, that means that they can live and die in isolation, as I said, and that's extremely powerful. So one way of thinking about this sort of way of designing your application is just think how a vending machine works. You might have this programmer. He's very like eager for coffee, and he wants to get his coffee. He comes up to the vending machine and he puts in like 1 coin. Let's say the machine requires you to put like two quarters in. He puts 1 quarter in. What's going to happen then? He will get a notification from the machines that add more coins, because it's sort of a validation error. He puts in 1 coin and presses coffee, and the machine says no. I mean you just gave me 1. I need 2. So. And if he then puts in 2, then he gets his coffee, right? But let's think if he comes to the machine the second day, it inserts his now 2 coins, and then now gets like an out of coffee bean exception, right? They're just thrown in his face. What would he do? I mean, most programmers, they don't know. I mean, actually, like where to get the coffee. I mean, we have Adrian. He actually asked him today when the coffee was out. He just ran down and bought more coffee. But that's not that usual, actually. Actually, that doesn't happen in Sweden. Then it's usually. So I think that's not what you would expect, right? You might get sort of a notification that we're out of beans, but you as a programmer or you as a user of this vending machine are not expected to go up and buy beans, pour it into the coffee machine, and then continue. Instead, I think that's completely wrong. So instead, this should be like sent out to a service engineer somehow, like a service guy. Through the beeper or something like that he might carry, and he goes in and fixes this, adds more beans, and then the programmer is happy. I think this is really the way we should design software. Okay, meaning that if we have a client and a service, the client asks the service for something, like validation errors should go to the client. I mean, things that the client actually are in charge of. If it puts in the bad email address or whatever, it's natural that the client should actually deal with that, right? But if there is an application error, it doesn't make any sense to just throw that into the users or through the user of the service face. He might have no clue how that thing is implemented, right? And just reading the docs or whatever, that's just wrong, I think. Instead, it should be a dedicated channel to someone watching that component, to someone that actually knows how it's implemented, if it's possible to do something in the first place. And if you look at how systems are usually written in Java, it is like that the application error is just thrown in your face, right? And the main problem is that there is not really much you can do, because if you write a regular Java application, then you have that single thread that's running your code is the only thing you got. Exceptions do not propagate across threads. So the only way to survive that context and not have like things like these cascading failures that we'll get if like the whole stack is blown up is to add your try-catch statements. And since things can fail basically anywhere, you need to add these try-catch statements everywhere. So it means that first it's scattered all over your whole code base, and secondly it's tangled with your business logic. I mean, the business logic might be very clean, but if it's like half of or more sometimes, like 70% is just error handling, usually not doing anything useful, at least in most cases. Very, very, very rarely I've seen actually a user be able to fully recover and know what to do with the exception being thrown. If we have a model where failure is isolated, you have these components that live and run in isolation, and have a mechanism of reifying failure as a message and sending it somewhere else. That means that then the failure can be dealt with somewhere else. Okay, this is extremely important. Then you don't need to, like, for all good reasons, like keep this thread alive because that's the only thing I got. So instead, application errors should go upwards in the dedicated error channel up to what we call the supervisor. Okay, and the supervisor should manage the failure. So this is very much how ship construction works. Have worked for ages. Like this page this is images from 1940 when they sort of built this USS Dakota. So I think the right way is, as I said, to reiterate, hammering in a point, isolate the failure, compartmentalize. Even if you don't use actors, this is a solid pattern that you should apply. Manage failure locally, and this will make you avoid cascading failures. So this way of working has a name called bulkheading. So if you want to read more about that. One example actually that some people bring up as bulkheading is the Titanic, you know. But the Titanic actually sank. But you know why? Because it didn't have proper bulkheading. These bulkheads, the walls in between didn't go all the way up. So when one of the compartments started filling up, and the ship started to like tilt a little bit, it spilled over to the next one, to the next one, to the next one, and the whole ship sank. So I think Titanic is really an excellent example of cascading failures, how to not do things. If you have fully isolated components, this cannot happen, right? So we need supervisors that deals with the problem, okay? And in Akka, you know, bringing these. Now we're coming back to this hierarchies, right? If I create a child, if I create an actor, he becomes my child. But not only that, in Akka, then I sort of supervise him. That is not optional, right? That's mandatory. So we have mandatory supervision. In Erlang, that's one of the design flaws, I think, of Erlang. If I should complain a little bit about Erlang, is that in Erlang is optional. We had that in Akka earlier, but users actually did it wrong so much. So we enforced it. You can't create an actor in Akka without having it supervised. It will be supervised by someone. If it's a system actor, it will be supervised by the top-level guardian. Okay. So how does it look? If you don't do anything, it's still supervised, because each actor has a default supervisor that does an okay job, right? Basically what it does is that if an actor fails, it throws it away, restarts a new one, and let it go. But I think, as I said, resilience is too important to just rely on defaults. It's actually the application semantics. So I think you should override that and define a supervisor strategy that actually has semantics, that actually deals with what the application is really doing. So in this example here, you can see we're creating a supervisor strategy that, in case of an arithmetic exception, then it's probably user input valid, something's wrong. Then I will just resume the actor and hope that it doesn't happen again, right? And the next time the user puts in something. If it's a null pointer, I probably have corrupt state somehow. Then I'm restarting. And if it's none of these, then it's something I didn't expect. Then I can't handle it. So what I'm going to do then is escalate up to my parent. Hopefully that guy knows, right? It's above my pay grade, you can say. I don't have enough knowledge or enough power to deal with the problem. One example is, for example, out-of-memory exception. That's not possible to deal with. So what's going to happen if an out-of-memory happens in B down there, right? It will escalate all the way up to the top-level guardian, and the JVM will exit. But the nice thing is that since supervision is based on message passing, and message passing works across machines, right, as across cores. That means that the failure model, the way you write your system, actually works equally with the same semantics across machines. So you can have this actor tree span multiple machines. This means that if one VM blows up, someone will notice. It's not just your regular like try catch. If it's not caught, it's like silence. The best you see is like stack trace in your console all the way up to your executor service. Right? It doesn't happen. Someone will notice, and someone will have to deal with the problem. Okay. Yep.
If you could back up one just so I can see that diagram again. So if B throws a foo exception, A doesn't know how to handle it, escalates. Can the top level supervisor then say to himself, oh, that's a foo exception. B, please resume.
No, he can't.
No.
He has to do that himself.
So he can't communicate back down with B?
No, but everything.
A could communicate with B until somebody's moving?
No, but each one. So no, he can't do that. I mean, it's only one level deep, right?
Oh.
So it's you have to design your application in a way that will deal with that.
Okay.
And I think it will be too messy to have a supervisor like jump hierarchy levels and do funky stuff. So. Okay, so in this simple case, the actor I'm creating with context, that's a child of mine, will be then managed under the supervisor hierarchy or supervisor strategy. Okay, so that is from the parent perspective. From the client, from the child's perspective, he can actually do some stuff. He can hook into the lifecycle callbacks to do something just before he's killed, for example, on a restart. Then he can clean up things using the pre-restart callback, and he can get the reason for things, so he know how to deal with that. And I say the same thing with the post-restart. Right before when a new instance is created, post-restart will be called, and before he just hands out to handle messages, he can do reinitialization and so on. And there are more callbacks than this. So now we talked about sort of the hierarchical way of managing failure. Sometimes you perhaps want to, if on the same level, you might want to monitor a child or someone else in the hierarchy to like see if that guy goes down. Then I know I should shut down for some reason. I have no purpose in life now anymore when my body's dead. And what you do then is that you use this context.watch. So you can watch another actor's life cycle by just passing in the actor reference to that into the watch method. And then you will get a terminated message as down here whenever the guy dies or exits somehow. Okay. You have threads and locks for scaling up usually, and then you have like some fancy clustering tools, messaging middleware or whatever to scale out, right? And that way you are very constrained. You can't move components around, and you don't have the flexibility to do things to change the topology at configuration time. Things are hard coded. I think that's completely wrong. You shouldn't hard code in the topology when you're into your application, when you write it, when you design it. It should be something that can be configured. You might want to deploy it in different kind of settings and with very different sort of ways of looking at how the application is deployed. And even more, when you have externalized it like that, you can actually change the topology at runtime, and this gives you the elasticity. You know, elasticity, that's the promise of cloud computing. You just spin up instances like really, really fast and you take them down. Yeah, okay, that's all nice, but our applications need to be up for the job to do that as well. And Akka is. There are other tools that are also that's really nice, but Akka is one of them that actually allows you from within make that happen, right? You can just add nodes and have actors be moved out and vice versa, shrink the cluster and so on. So I think you need to deal with scale up and scale out, and they are, as I said, essentially the same thing. To reiterate what I said in the intro, we need to minimize contention and maximize locality of reference. And share nothing really is the way to go here. That gives you both of these things almost for free, at least if you have a very efficient implementation backing these concepts. If you don't do that, Amdahl will come down and hunt you down. I mean, he will hit you in the head hard. like Martin Thompson said that, if I can quote him, I mean, scalability is the house where Amdahl wakes up early in the morning and rules with an iron fist, right? So, and if you doesn't know Amdahl's law, it's essentially saying that you're limited by the speed up of your application. So if your application is 95% parallel, if you look at, it's hard to turn around like this. If your application is 95% parallel, that's pretty good, right? If 5% is not parallel, it might be your, I don't know, I mean, your database calls or something like that. Then, in this case, I mean, the actual accesses might vary depending on the application, of course. But in this example here, you're limited to a 20% speed up. In this case, at 1024 cores. if you go beyond that, it doesn't matter how many cores you add. You can add 1 million cores. You will not get more than 20% speed up. And if your application is like 10% not parallel, you're limited to 10% speed up, and so on. So it really, really matters that your application is reactive and event-driven and non-blocking all the way down. Every single layer needs to participate. Else, yeah, you know Amdahl's coming. So how do we deal with scalability in Akka? We have various ways. You can define an actor to be a router. For example, that means that he won't process any messages himself. Instead, he will create children, fan out work to all of these children. We have various strategies, sort of routing, algorithms. Round robin is one that I'm showing here. You have random, broadcast. We have like scatter, gather. There are also some very interesting cluster routers that are fully adaptive, looking at metrics, how the application is being used, like CPU, mailbox sizes, and RAM and stuff, and you can configure sort of the thresholds, how it should act. If you should like spin up more and so on. A router can also be pooled, and you can set like max and low watermarks and stuff like that. All right. But what's also very interesting is that you can do that from the outside, and you can do it from code. It doesn't matter. Sometimes you want to do both. You want to give good defaults in the code, but you also want to override those from the configuration file. Akka's using type-safe config library. That's a Java config library that's brilliant, written by one of our engineers, Havoc Pennington. It's actually starting to be used way outside, not just type-safe, not just Scala, but also across the whole Java ecosystem. I really encourage you to take a look at it. We use it, Play uses it. So this is an example of how it can look there. So here you see also, here are the names come into play. Here I'm saying path to actor. That's like my path, like A/B/C. That's the path of this actor that I want to now configure. Okay. So if routing is not enough, if I want to like really scale out, not just up, then we can just turn on clustering. That's also done in the configuration file. You just say that my actor provider should be cluster actor ref provider. And of course it has more configuration options if you want, but it's really, really simple. Everything is driven through configuration. And then you have a whole set of cluster routers. And the only thing you do then is you add this cluster section here. Then you can say, for example, I want to enable it. I want to have like max number of instances per node should be 3. That means that whenever you spin up new instances, it will deploy 3 new workers of this router on that new instance, but no more, right? And so on. We also have other tools. We have cluster pub sub, which is a very nice pattern that we have in the contrib library. So in this case, you just create like a distributed pub sub extension. You get the mediator, and through that mediator, which is also an actor, you just send it a message, say subscribe on a specific topic, and then you register yourself. Self, by the way, is myself. It's my own actor ref. I should not use this in an actor, because then my this is sort of one of the corner cases, one of the things you should watch after. Because if you publish this somewhere, then someone might actually be able to access your state from the outside. So you should always use self. So here I'm publishing. Here I'm subscribing to the topic content. And from someone then writes to this content, he just gets the same mediator, and he says mediator publish, and sends the content and some message, right? And then everyone, regardless where they are in the cluster, will just receive that message. And if you spin up more, they will receive the next message that's being sent, and so on, right? It's fully elastic. You don't need to configure anything. Things just work. As many nodes in the cluster you have. Or, pardon me?
What types of objects are you allowed to pass to?
Yeah, the question was what type of objects. Yeah, you should not use Java serialization for sure. I mean that's a really bad way. It doesn't have any versioning, so you've got versioning problems. It's really slow for demarshalling and marshalling, and so on. In Akka, our protocol is based on protobuf. I mean, that's a great one, right? But you're not constrained to protobuf. We have a whole set of serializers, and all those are configurable from the config library as well. Or you can write your own. right? It's easy to write your own. Same thing with routers. You can just write your own router if there is an algorithm that you want that's not there. So Akka is very extensible, definitely. So other cluster feature that I don't have time to go through is that cluster membership is something you can hook into. You can actually subscribe to messages when nodes come and leave and when they become available and not available and so on. We have a concept of a leader. We also have cluster singleton pattern. If you really want to have one guy in the whole cluster and make sure that it's only that. I don't know. I mean, if you want to like spam send emails to your users or whatever, you perhaps don't want to do that on every single node, right? It will be duplicated by how many nodes you're currently running, right? You want to do that from one single place and have a single writer there. And that can be done. But singletons are of course a bit tricky, and you shouldn't use them too much, right? Because you get contention that we don't want. We have cluster roles and cluster sharding, if you want to like split up your cluster in different regions and stuff like that. All that works. It's really nice. So, yeah, I'm running out of time. So how much should I go on? Okay. You can, huh?
You go.
I go. You can leave if you want. I won't be offended. I would probably have left by now. Akka persistence. That is the last thing we added in that we've been working on the whole fall. And to just give a short overview, I'm really excited about it. It really fits. It really sort of adds a missing piece in the Akka sort of landscape, right? I think. It doesn't do persistence on, I mean, the actual persistence on disk, I can say. It has a whole set of journals that actually does that with various implementations. So it's really not a really full-blown, it's not a database or anything, it's a pattern that we've seen clients use, I mean, over the years. It implements event sourcing, CQRS style, and it does that through two different models. Command sourcing, which means that you will get at least once guarantees, and event sourcing, which is the opposite, at most once guarantees. Sometimes you need either or, right? And sometimes you can use them together. And we used to have something called Akka durable mailboxes, which we now have deprecated. This is it's a way better replacement for those if you used those earlier. You can use this for like replication. You can use this for a lot better sort of. So I wouldn't say guaranteed delivery because I don't believe in that, but a lot reliable delivery really, and the building blocks here is that event sourced, and they're called the event source processor, and we have the processor is just the command sourcing, right? We have some other interesting things. We have for example a view component that you can just basically for free just hook in to listen on the same journal as the processor, and this is perfect for like for a CQRS, like command query segregation, if you know what that is. Or for replication or something like that, like to listen in on an event stream and do something without affecting it. So the benefits of Akka persistence, I'll say, is you have a sort of, the nice thing is that every single state change, everything that happened in the actor system is persisted. That means that if you have like bulletproof historical record, nothing is lost. As I said in the early. In the first 10 minutes was that you know that disk is really cheap and RAM is cheap. There's no reason to throw away data anymore. I mean, all these classic SQL databases, right? They use the in-place update. There was a reason they did that, because memory had very constrained memory. But I think that's fundamentally the wrong way to approach the problem nowadays. There's no reason to throw away data. I mean, Pat Helen said it really well. Then he said a classic like a relational database is just sort of a snapshot of a cache of the event log, a cache of the snapshot of the event log, right? So it's a very limited view of what's actually have happened in your application. Everything is there in the event log. Why not persist that instead? and then have for example, a view, right, reading the event log, updating your database for querying. That's CQRS, for example. Then it's as free, it's actually literally free to put in like a view listening to the event log for auditing, or for replication, if you want to replicate the event stream and do something over here, and so on. So it gives a lot of flexibility. It's easier to test the systems, I think, as well. And you don't have this object relational mismatch, in which you have your event streams. They are materialized as objects, and then you have this clunky thing you need to persist. When you have this beautiful event stream, and the interesting thing is that databases, they are using event logging, append-only log, really efficient logging structures under the hood. That's how they are implemented. It's just that the only tools that you're giving are in-place updates, where you actually lose data every time you do an update. And need to go like all funky stuff to keep history around, right? I think that's wrong. And I think that Akka persistence is one nicer way of solving the problem. I don't know if I should go into detail. I'm running a little bit out of time. Patrick at the Akka team, he did an excellent webinar on this in depth. So is it recorded yet?
Yeah, it's available already.
Yeah. So you should go and see that instead. It's like 1 hour in depth of Akka persistence rather than me just rambling about the same things. Yeah. You have to read this paper though. I mean, it was extremely influential paper by Patel, and Patel is the guy behind. He worked with Jim Gray on tandem systems. He knows this stuff. He knows transactions really. He was like part of the system that really built these. I mean, those are sort of pioneered transactions. But he doesn't believe in transactions any longer. Distributed transactions are just broken, right? If someone like Pat Helland even goes out on record and says that and argues for, like he does in this paper, for a model where you have these share nothing entities that forms the sort of the consistency boundaries, right? Because some people ask about what about transactions in a system like this? So the way you sort of define transactions, the way you model your system, is that you work with in DDD's language they call aggregate roots. An aggregate root is like a facade to one entity or a set of entities, and within this you have strong consistency, right? But it's too expensive to have full consistency in your whole application. Then you can't stripe things, then you can put things on multiple machines or whatever. So then you have eventual consistency between these aggregate roots, and that have implications on design. I mean, things are not always easy, right? If you want to really scale systems, and then you need to think, right? Tough luck, right? You need to think about the problem in a slightly different way. But I really believe that if you do this, there's basically no limit to scalability, because you can actually scale as many nodes that you have, because you can fully stripe things, and each aggregate root can have their own journal, which use the single writer principle to minimize contention, just writing like crazy to this journal, uncontended. Right, so there's a lot of good things coming out of using the right patterns, I think, if you have a solid platform supporting these patterns. Okay. Yeah, I was actually planning doing some live coding. I'm not going to do that now because we were running out of time. I was planning on doing, I'm sort of persisting this game of ping pong. First using a processor and then using an event-based processor. But I'm going to leave that as an exercise for the listener. I can give out the sort of the right way of doing it later on. If we can compare, right? So anyway, so if we're still going to look at this just briefly how it looks. So if you have a regular actor, you can just swap the actor to not extend actor, but instead extend processor if you want to use command sourcing, or swap to event-sourced processor if you want to use event sourcing. So the difference between event sourcing and command sourcing, if we're going to explain it briefly, is that with command sourcing, you persist ahead of time. Ahead, before the actual event enters your system, you're persisting it, right? And this means that if there is, you actually do it even before validation, right? That means that that when the event then enters the system, things can actually fail, and things might actually do side effecting, right? So either use idempotent messages and command sourcing, but if that's not possible, then you should rely on event sourcing, because event sourcing decouples state changes from side effects. So with event sourcing, you actually receive the outside stimuli, some sort of event, then you do your state change, and then you create an after the fact event. This has happened. This is the fact, right? For example, the ball here. If I would receive that, I would first then update my state, and then I would, if that went well, I would generate a ball received event. I would persist that event, and then run my side effect. In this case, printing something out, and then also like sending the ball to my buddy again. So they are very different approaches, and you can use them together if you like, and they have very different purposes, but depends on what your application need to do. So if you use a processor, the only thing you need to do is you have to wrap the message in persistent and then send it off. It means that you can actually distinguish between persistent messages. You see at the bottom here, I'm sending a persistent foo to this processor. That will be persistent journal. If I'm just sending a regular string, it's not persistent, and then it will not be journal. So you can distinguish between these. With event sourcing, you don't need to wrap things with persistent there, because it will just accept regular messages and then generate events under the hood. So in a way, I sort of like event sourcing better, but because it's cleaner, I think. Yeah. The application, yeah, you generate the events. You're in full control. The question was if the events are generated under the hood, and so that's not possible, because I mean it might be that one command coming in can generate one event or 10 events. I don't know. That depends what you want, how you want to like split it up, and how you want to define the semantics of the application, right? So that is very different. So yeah, the view is also just an actor. And it subscribes on the same processor ID as the processor it wants to read from, and then it reads directly from the journal, so there's no overhead at all. It's really listening in completely free. The channel we can skip. Yeah. So skipping the demo. Responsiveness, as I said, nothing this would matter if our systems can't be responsive at all times, I think. When things go well, yeah, that's easy, right? But especially responsive when things fail, or when there are unpredictable things, right? When there are spikes or whatever, when things happen that we didn't know was going to happen. And I think that there are some nice ways, some sort of well-established patterns to deal with this. Like back pressure is one of them, and Akka has that built in its mailboxes first. You can define, I haven't said that, but you can actually define which mailbox your actor should have. If you should have like an unbounded mailbox, that is actually the default, but it's not a really good general purpose thing, because it doesn't have this boundedness, right? You can actually run out of memory. So it's better to like think things through. What kind of guarantee should I have, and so on, and have a bounded mailbox. You can also build in things like we have a circuit breaker pattern, for example. When things go haywire, you can actually back off and do something with the exceptional situation, and then retry, and so on. The dispatchers, our scheduler have lots of configuration options as well that helps you deal with these things. I usually try to apply Little's law, if you know about that. So you can look it up, but that's a really nice sort of small sort of mathematical model in which you can sort of measure latency, or actually measure response time, and see where you should actually cap your queues in order to be able to maintain the SLAs that the application requires.
Litways?
Yeah, go to the Reactive manifesto. There's a link there, right?
Okay.
So or just Google it. Little's law. Little's law. Yeah. Yeah. So here's a Reactive manifesto. So most of the things I've talked about here, I mean, that talks about principles are actually defined in this Reactive manifesto. We built this. We started this Reactive manifesto just to get a common vocabulary, to have one single way of talking about these things, to have a way of categorizing what we think needs to be done to be able to solve problems today, right? And because, as always, I mean, when there's a need, I mean, solutions pop up. And different solutions have popped up in different or communities, in sub-communities or larger communities, different languages or whatever. And all that is good, right? Diversity is a good thing. But from the user's perspective, for you guys, I mean, you might get really confused because they talk about things in different ways. Reactive manifesto is a way to bring the communities together, have one way of talking about things that makes sense. And also advocating, I mean, trying to educate sort of people about what we believe in, at least. So TypeSafe is an excellent, as you probably know, I mean, reactive platform. Akka is one piece in the puzzle. We also have Play, that is reactive all the way down, gives you like reactive composition of the web. Of the web request. It has like nice support for streaming in a fully non-blocking fashion, and so on. It's all based on Scala as well. I mean, that's why we're all here, right? With that Scala meetup. Scala is our secret sauce. It's really what makes this happen. What really enables us to do all this really cool stuff. I think it would be a lot harder in Java, actually. So, and if you want to try things out, you should download a TypeSafe activator. We have around 80 different templates now, covering basically everything you might want to do. I mean, we are covering the latest like Akka persistence stuff, covering like persisting with Mongo or with anything there, covering writing applications using Knockout.js, Angular, and like Spark for big data and whatever. And it has a really nice UI. I don't know if you've seen it, but it gives you this interactive tutorial thing, right, where you can actually edit the tutorial in a way, right, and see changes happen. And if you're really happy with the result and want to go on, you can just take that project. It's a really solid, real SPT Scala project you can just continue working on. So it's also like a templates for bootstrapping applications. So, yeah, thanks for your patience. It was a long talk, and I didn't have even go through my second demo. So, yeah, question.
Question. That's a great overview of Akka. There are some similar systems. So there is, for instance, Finagle running on top of Mesos at Twitter, and I know that the futures kind of converged. How do you see Akka versus that combination? And on the other hand, we see Spark coming up, which is kind of big data, but it's also going in the same direction because it's already resilient, yeah. And it has Spark streaming, which is kind of responsive. So I wonder, what is your take on how these three things kind of will evolve in Scala ecosystem?
Yeah. So the question, if I should repeat it, was I mean, we have Akka, we have other like tools solving similar problems, like Finagle, like Twitter's Finagle, and like Spark, for example. And I think one thing that we try to work with, I mean, was bringing, for example, Twitter in, like we did with the futures implementation. They used to have their own futures, and that doesn't make any sense. Like futures is like a solid thing that should be in the Scala library. So we started this specification, and Twitter was part of it, and we actually agreed on something that we think are good. And we all use it now, and that's in Finagle now. I think it's at least coming. They're always like one version behind in Scala, so I don't know exactly the details there. But I think more of that, right? Same thing. We're thinking hard now on how we can do streaming in Akka, for example. And we're not really there yet, but we're talking to companies. We're talking to Spark. I mean, Matei there, and we're talking to people, and they're I mean, sort of. It tends to be about the same time that similar problems pop up in many different places. I just want us as a community to talk more and join forces on single solutions rather than just reinvent the wheel all the time, because that doesn't help with interoperability. So we really try to encourage that. I mean, and try to be open as TypeSafe and in the Akka community as well for for like standardizations, if you may call it, right? Makes life easier. Yep.
Is there a contract that that the journaling implementations have to fulfill to guarantee resilience? They have to guarantee that they replicate the data so that there's no failure in the journaling.
Yeah, the question was if there's like an SPI for the journal, right? If you want to, that you can implement, and yes, there is, and it's fairly small. I mean, I can show you the code. It's just a few methods, and this is what have enabled the community. If you go to akka.io/community, you can see that's like more than 10 different journal implementations already. All written by the community, and we even have customers that have written proprietary ones for their like custom backends. And it's really easy. It's just delegating it from a fixed set of methods to whatever backend they have. And of course, I mean, in the end, it's the guarantees that the backend give you, how durable things really are, right? But it should be fairly easy, yeah.
Last year, Reactive acquired Spray. So how Spray played in the whole Reactive tech stack?
That's a very good question. Last year we acquired Spray, yeah. Spray, if for you that don't know about it, is according to the latest benchmark, is the fastest sort of HTTP library there is on the Java platform. I mean, not just Scala, but on the full Java platform. And so we're really excited when we were able to start taking advantage of that. So what we've been doing the fall and now is to have Matthias and Johannes, the guys behind Spray, to improve what they have and to make it fit very nicely into Akka. So they've been working on that for the last 6 months, and it's going to result into the new Akka HTTP module. It's going to be released in a few months. Basically Spray, but even better. Now this is, for example, where we're looking into consolidating things like streaming, for example. Akka.io used to have a pipeline abstraction that we deprecated now, and because we know we're onto something a lot better, and that's something that we're going to like fold into Akka HTTP, for example, and Akka.io and a lot of other places, perhaps even Play, and so on. So a lot of good stuff coming. No more questions? Okay. Thanks for listening then.